Hi, I'm Elliot Oblander. I'm a senior in Wharton, studying statistics and actuarial science. Today I'm going to be talking about my thesis, which is entitled Population Movement in Japan, a Hierarchical Bayesian Approach. My thesis advisor is Shane Jensen, Associate Professor of Statistics. To contextualize this project, we first consider the current state of Japan's population. The fertility rate in Japan has been well below the replacement rate for several decades, and the population has declined by nearly 1 million since 2010. About a quarter of the population is over the age of 65, and the overall population of Japan is expected to decline by over 30% in the next 45 years. However, digging deeper into these aggregate trends, we can see that there's a lot of regional variation in population change. For instance, Tokyo has seen a steadily increasing population since 2000, whereas Akita, which is a very rural region of Japan, has seen a steady decrease in population. The main driving force behind this is urbanization, which is that people are moving more and more out of rural regions into urban regions. And in particular, younger people tend to move more, which leaves elderly, less mobile populations isolated in rural areas. As such, we're focusing on the spatial variations in this project. In particular, we're looking to model migration within Japan. The maps on this slide give an illustration of this trend. These maps both use census data as of 2013. On the left, we can see a map color-coded by population density. On the right, we can see the proportion of the population in each prefecture that is over the age of 80. We can see from this that the very rural regions with low population densities also tend to have the highest proportions of elderly residents. For this project, we're modeling net immigration rates into each prefecture from other prefectures of Japan over the course of 10 years from 2004 to 2013. This graph illustrates for each of Japan's 47 prefectures the net immigration rate over the course of these 10 years. These numbers don't include immigration in and out of other countries. It's only looking at population movement within Japan. This map further illustrates urbanization. We can see that very dense prefectures like Tokyo are having more and more people move into them, while regions in the countryside are seeing a net decrease in population. Our goal for this project is to perform a descriptive analysis of population movement in Japan. In particular, we want to understand what census and economic variables are most associated with net immigration rates. Additionally, we want to decompose variations in immigration rate into observed and unobserved differences between prefectures. Furthermore, we want to look at what the effects of the Tohoku earthquake and the subsequent nuclear meltdown were on net immigration rates throughout Japan. Lastly, we want to be able to predict immigration rates for future years. To model this data, we use a fully Bayesian hierarchical regression model. This model allows for random intercepts, which lets prefectures vary from each other according to unobserved differences, covariate effects, which allow for the explanatory effects of census and economic variables, and contemporaneous shocks in 2011 due to the Fukushima nuclear meltdown and Tohoku earthquake. We use normal priors on the intercepts and then use spike and slab priors on the regression coefficients. We give the model hyperparameters, non-informative or weakly informative priors. We estimate this model using a Markov chain Monte Carlo sampler and do several robustness checks on the in-sample and out-of-sample performance of the model. We also test it against several alternative model specifications. Based off of our tests, we find that our proposed model has the best in-sample performance and also gets comparable out-of-sample performance to alternative model specifications. Based on the fitted value plots, we can see that the model performs very well in sample with an R-squared of nearly 94%. More impressive, however, is the model also gives robust predictions out of sample, even for cases where the prefectures aren't previously observed. With a robust model in place, we spend the rest of our time discussing what we can learn from this model. This map gives the posterior mean intercept values for each prefecture of Japan. What these values essentially tell us is how much variation there is between prefectures that can't be explained by our covariates. These maps show the effects of the 2011 nuclear meltdown based off of the model. We can see that Fukushima has by far the strongest effect, while other regions of Japan tend to have mostly positive effects. This is consistent with what we'd expect, since people moving out of Fukushima have to move in somewhere else. And so we see that Fukushima and some of the surrounding regions experience negative impacts due to the nuclear meltdown, whereas other regions of Japan experience slight positive effects as people evacuate from those regions into the other regions of Japan. This table shows the covariates which were significant at the 5% level based off of our model. We see that many of the covariates have to do with labor and job availability, and in particular we see that some of the most predictive covariates are the ratio of job openings to job seekers and the percent of high school graduates getting a job outside of the prefecture. This is consistent with what we'd expect, which is that people are moving between regions of Japan based off of career prospects and job availability. Next, beyond just looking at the inferences from the model, we'd also like to be able to test the model's ability to predict beyond just the in-sample data. We only have covariate data up to 2013, and so any future predictions requires also modeling the covariates. So in this example, we just use simple linear time trends using a hierarchical Bayesian specification for estimating the time trends, similar to how we estimated the full model. The plot on the right shows the fitted values for 2014 through 2016, for which we don't have the covariate values, but do have the actual immigration rates. The R-squared is about 80%, which tells us that we don't lose much predictive accuracy even when we're extrapolating the covariates. Taking the method that we use to predict the immigration rates for 2014 to 2016, we can further extend that out to a longer horizon. This graph shows our predicted immigration rates for each prefecture of Japan through 2020. We can see that most regions are predicted to have a slightly increasing or roughly constant immigration rate, but Tokyo is predicted to have a slightly decreasing immigration rate. However, beyond just looking at the mean predicted values, we'd also like to look at the uncertainty in the predicted values. These charts give illustrative examples of showing the uncertainty in predictions. The chart on the left shows the predicted values for Tokyo up through 2020. We see that Tokyo is predicted to have a slightly negative trend in immigration rates, but its overall net immigration rate is expected to stay positive. On the right, we see that Fukushima is expected to stabilize after the 2011 disaster, but is still expected to have a negative immigration rate over the next several years. While these are only illustrative examples, it's simple to get similar predictions and confidence intervals on the predictions for all other regions of Japan and up to any arbitrary time horizon. We can also use more sophisticated covariate imputation methods in order to see how immigration rates might vary under various counterfactual circumstances. To summarize, we've modeled net immigration rates between prefectures of Japan based off of a hierarchical regression specification. Through this, we've been able to isolate variables which are most important in predicting immigration rates between regions of Japan, and we've also allowed for variation due to latent differences between prefectures, as well as anomalous effects after the 2011 earthquake and nuclear meltdown. We've also provided a framework for predicting future immigration rates, and our predictions are seen to have robust accuracy. And the framework is very flexible, which also allows us to extend to counterfactual analysis and more sophisticated methods for extrapolating the future values of covariates. This concludes my presentation. For technical details on the model specification, and for additional discussion of the results of the models, please see the full paper. Thank you for watching.